Salutations! This is a problem from the 1965 book 100 Great Problems of Elementary Mathematics by Heinrich Dore, originally published in 1958 in German under the title Triumph der Mathematik, or in English, The Triumphs of Mathematics. This problem invites us to discover the locus of a marked point on a circular disk that rolls along the inner edge of a disk of double its radius. The term locus in this case refers to the line traced by that point as the disk rolls. This mechanism, a circular disk that rolls along the inner edge of a disk of double its radius, is known as a Tusi couple after the 13th century Persian mathematician Nasir al-Din al-Tusi, although the 16th century Italian mathematician Guillermo Cardan independently reinvented it. The term Tusi couple only dates to 1966, hence why this book, published in 1965, refers to it as Cardan's Spur wheel after Guillermo Cardan. First, we create the larger wheel and constrain it to a radius of r. Then, we create the smaller wheel and constrain it to have a radius of r divided by 2. Now we're going to make the smaller wheel tangential to the larger wheel so that it will roll along the inner edge. By creating a line segment along the line of tangency, we can specify the angle and create a rotation. Let's change the animation mode so that it repeats continuously. As per the problem, we need to mark a specific point on our circle. I'm going to do this by creating an n-gon, which will also let us visualize the smaller wheel rolling. Now I'm going to specify an angle betwixt the tangent line and one of our marked points. The smaller wheel is half the circumference of the larger wheel, but must trace the same circle. Thus, as there's no slippage, the angle of a point on the smaller wheel relative to the tangent line will be 2 times theta. We can visually check it out to make sure it looks right. Now we can trace the loci of points on the circle, and we find, remarkably, they all trace straight lines. This mechanism, called the Tusi couple, is an example of what is called a straight line mechanism that converts a rotary or angular motion into a linear motion. There's a really cool Wikipedia page with other examples of straight line mechanisms that I recommend checking out. Here's another problem from Triumph der Mathematik. We are asked to find the envelope of a straight line, 2 marked points of which slide along 2 fixed, mutually perpendicular axes. The envelope is a similar concept to the locus. Mathematically, it refers to the curve tangential to every member of a family of curves, or in other words, the various curves resulted from varying a parameter. It can be thought of as a linear variant of the locus tracing the outer edge of a curve as it moves. This particular envelope is called the astroid after the Greek word for star, for reasons that will soon become clear. It would be quite easy to create the astroid in geometry expressions, but I'm going to show you an alternative way of constructing it using a mechanism similar to the Tusi couple that we just saw. So here's our beautiful Tusi mechanism that we just created, and what we're going to do is change the radius of our smaller wheel from r over 2 to r over 4. This trace looks really cool, but unfortunately it's no longer correct. As you can see by the animation, the smaller wheel no longer rolls at the correct rotational speed. This is because the circumference of the small wheel now is 1/4 of that of the large wheel, so now its rotational speed needs to be 4 times theta, not 2 times theta. Now we can visually check it to make sure that the small wheel rolls properly. It's really amazing how much visual calculus humans do inside of their heads without thinking about it. Let's isolate one specific point's trace from the noise. What an interesting shape! It makes you think of, perhaps, a star. Now we're going to calculate the implicit equation which Geometry Expressions nicely does for us. As the result shows you, doing this by hand would be a very unpleasant time. Forgetting everything we just did, let's construct the astroid according to the definition given in the book. The envelope of a line of fixed length which slides along two mutually perpendicular axes. We can use the x and y axes as our mutually perpendicular axes. We need to constrain the line with a length constraint to make it a fixed length, and one of the points we need to constrain with a coordinate constraint so we can make it slide along the axis. By varying point R's position on the x-axis, we get a series of resulting lines. By using Geometry Expressions' trace feature, we can visualize all of these resulting lines. Note that every point on this trace has two solutions, of which only one is shown. The end of the line segment on the y-axis could be negative or positive. We'll now calculate the envelope by selecting the line and the Construct Locus option. The envelope is simply the outer border of the trace. As you can see, the envelope exactly follows the bottom half of the locus of point E on our disk mechanism. Remember that mathematically there's two solutions for each point on the trace, so the full mathematical envelope exactly mimics the locus we obtained through the disk mechanism. Calculating the implicit equation of the asteroid verifies that the lines are identical. This method of constructing the asteroid by rolling a disk along the inside of a disk 4 times its radius is called the hypocycloid construction of the asteroid. What an elegant example of geometric duality. Thanks for watching.